Okay, now let's solve our benchmark problem using a new mesh generation method, right? So I copy our code, Control A, copy, paste, save. I write them to the try to save. So here, as you can see, V0, WH, here we generate the connectivity list. Instead of this code, I use this code. Just I call the Delanoy function. Copy and paste. Here I write a comment, triangulation. So now we have points and we have connectivity list, and if I run this code, you can see the analytic solution, mesh, and finite element solution here. So now I want to do interpolations. What is the value of voltage for an arbitrary point inside the mesh? For example, this arbitrary point, 0.8 and 0.8. I want to find the value of voltage for this point. I can use the as we say the point location function to find the corresponding triangle. So the point location function, the first input is tr and the second input is p. So I copy this, and what is the triangle ID is equal point location. What is tr is a triangulation. Let me click on this. You can see triangulation, we should have T and P. So we have triangulation, and I write connectivity list transpose and P transpose. I think right here you can see the input type. P should be M by N. M is number of triangles, right? So we should do something like this. So here I write TR, triangulation, and 0.8 and 0.8. So if I run this code and write TID, the ID is 117, right? The ID of this triangle. Actually, as you know, here is 0, 1, and 0.8, 0.8 is here. So let's highlight that triangle. So actually here we plot the mesh, right? Here we plot the mesh. I write here figure 1, our first figure. And at the end of the code, I want to highlight the corresponding element. So this is triangle ID. And if I write colon and triangle ID, face color red, so I can highlight. This is our triangle that we are looking for, right? 0.8, 0.8. So now I should be able to calculate the electric voltage. So how I can calculate electric potential? First of all, I should map this triangle onto the reference triangle. Then I can calculate. Like these functions, interpolate 1D or interpolate 2D. So I copy this, paste, I write interpolate two-dimensional 1 degree. So for two-dimensional problems, we have points, connectivity list, and desired points, right? Desired points that we are going to have the electric potential on these points. And also this is the solution vector V, electric potential. So like this, first of all, we should find corresponding points, desired points, right? IDs, and for each ID, I should calculate the value of electric potential. So here, the output Y is equal to length of this. I write actually number of points. This is the output. So here I write the save interpolate to the one, and here I should calculate coordinate of desired point in reference element or in reference coordinate system. So, we had this transformation, this map for linear triangular element, right? This map. So, here I can write for each point, zeta is equal to, actually I should use the transpose function because we are looking for the value of zeta and eta, and we have the value of x and y of the triangle. So here I write that or determinant is equal to this product x21 y31 x21 y31, or I can write x1 is equal connectivity list 1 p 1 and connectivity list 1 and triangle ID I, right? The triangle number I for this point. So this is the index of the point, the first point of the triangle, and x coordinate. So this is x1. I copy this, paste. So this is y1. This is 2. Right? So I copy, paste, 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 paste. x21, x31, y21, and y31. So I copy this, and here minus, this is 1, 1, this is 2, and actually this is the same as x1. Minus x1. This is 3, this is 1. This is minus y1 minus y1. 2, 2. This is 2, this is 3. 2, 3, 2, 3, right? So now this is the determinant x21, y31. I write x21 times y31 minus x31 times y21. So what is the value of zeta and eta? Is this product. Actually, zeta is equal, you can see y31, I write here y31 times desired point, x and y, coordinate of the desired point. So here is desired point, the x coordinate. Actually, also I can write this. X is desired point, I and 1. Y is the y coordinate of the desired point, y and 2. So this is y31 times x minus x1. So x minus x1 is plus minus x31 minus x31 times y minus y1, y minus y1. So this is zeta divided by determinant. So the value of eta is pretty the same. The value of eta is minus 21 times this. I write here minus y21 plus x21 times this, or x21 times this divided by determinant. So this is the value of eta. So we have the value of eta and zeta. So n1, n2, and n3, like before, right? What is the n1 for triangle element? We studied it before, right? This is the value of n1 that we have it here. n1, 1 minus zeta minus eta. I write here 1 minus zeta minus eta, and n2 is zeta, n3 is eta. What is the value of yi? Is n1 times the voltage of each mesh node. I write here Vn, connectivity list of 1 and triangle ID I, the first point of this triangle. The second point, so this is 2, and finally the last point times n3. Save. So let me use this function to find the value of voltage at the end of this code. So this is V, and here is our desired point, 0.8 and 0.8. So if I run this, the value of voltage here is equal 0.45. Let's check with the Ansys Maxwell software. Here is our box problem, right? And what is the boundary condition that we used before? The boundary condition is this one. Let's check. we applied continuous boundary condition, right? This is a fixed boundary condition, and in our last analysis, right, this is discontinuous. So this is the solution. And now if I place a point here, actually fields, marker, add marker, here you can see the value of electric potential, right? So if I consider 8 by 8, actually 800 by 800 millimeter is here. It's right. So can you read the value of voltage? Let me zoom.
It's 0.4778.
Right. The value of voltage, right? So here we didn't use a fine mesh. So if I increase number of mesh nodes, 20 by 20, and run the code, right? 4, 5, 6, 3. We are using linear elements, right? If we use triangle elements, we can find a better solution. Right. But the result is close. The result is close. Right. Actually, around this point. Minus 0.4 or 4.5 e to the power minus 1, right? Close. So now we are able to find the value of voltage on each arbitrary point in our solution region, right? So you get the idea. We generate a mesh. No matter our solution domain is convex or non-convex, we can use Delanoy or Delanoy triangulation function. We solve the problem. After that, we should find the corresponding element that our arbitrary point exists on it. So we can use point location function to find the corresponding triangle ID, to be able to do interpolation. And this code inside this for loop is clear. It's a straightforward, right? So now if you want to be actually more confident about the code, you can do something like this. I can remove field, marker, clear all. I can plot this arbitrary line. Here, this arbitrary line, not the previous one, this line, right? Or more complex. I set the value of the first point equal to 0.1 meter and 0.2 meter and 0. Apply the value of second point, 0.8.9. Pretty arbitrary segment inside this solution region, right? And now let's consider 15 adaptive passes and solve. So you can see the solution and the voltage distribution here. Also, I can plot results, rectangular plot, polyline 2, plot the value of electric voltage, right? Also, you can check if you can get this curve in MATLAB or not. So I write here at the end of this code, I write xi linear space from point the same as this segment that we have. Point 1, point 8. I write here point 1, point 8. How many points we have here on this plot? 1, 0, 0, 1, right? So I write here 1, 0, 0, 1. And yi, arbitrary points from, what is the coordinate? 0.2 to 0.9. 0.2 to 0.9. Then I should use this xi, yi. So the first row, the second row transposed. So I can write the value of electric potential for these arbitrary points. So if I run the code, you can see the value of voltage. So why we have 0? Only we have the value for the first point. Maybe because of this. Because we used y coordinate here. Let me use another syntax, vi, right? So the same name for this parameter. So now let's try. And this is the value of vi, or vi transpose, equal to vi transpose. So let's check. Like before, let's use the Excel and export this data. Report, export to this desktop app, save, yes. And let's copy, this is millivolt. So control copy, paste, plot, right? This is calculated by Ansys Maxwell. This is our calculation. VI. This is in volt. If I want to have it in millivolt, I should multiply it by 1e3. So here is the value of VI. Copy, paste, and plot. Yes? Using the MATLAB, we generated the same graph. Right? Now we are able to solve a problem, and we are able to post-process it. We are able to find the value of electric potential for each arbitrary point in our solution region. So we should use this procedure to be able to calculate this summation to be able to do error analysis, right? To be able to do error analysis for our benchmark problem. Actually, this equation that I will explain it later.